All right. Let's get started on finishing up lesson 1.3. And if you recall, we've looked at limits involving infinity, and we've even looked at limits at a point. So I want to review with you guys the definition of continuity again, okay? Continuity at a point. Okay? A function f of x is said to be continuous at a point x equal a if and only if the following are true. 1, the function f of a exists. 2, the limit as x approaches a of f of x exists. Oops, excuse me. Exists. And 3, the limit as x approaches a of f of x equals f of a. Okay? Now what we have seen here, yeah, there we go. Well, let me see, can I not scroll this thing down? All right, well, I guess I'll have to keep it in this screen right here. Okay, so that's the definition of continuity. So now we are going to look at numerical determination. Numerically determine the limit. Okay? So we're going to numerically determine the limit. All right, so let's determine numerically the limit as x approaches -2 all right. No, unfortunately, I'm not going to be able to show you the calculator on this lecture. So what you're going to end up doing is you're going to end up plugging this function into, you're going to end up plugging this function right here into f of x. In other words, this function right here, f of x, and you're going to plug that in to your y1 in order for us to determine the limit as x approaches -2 of this x squared minus x minus 6 over x plus 2. So how are we going to do that? Then we're going to actually fill in a table. So we're going to approach -2 from the left, which means that you're going to have to go into your table and your calculator. Okay? And this is your function right here, f of x. We're finding the limit as x approaches -2 from the left. So we have to come close on the left. So we get -2.1. Now, if you look at your calculator, you're going to have a -5.1. All right, making sure that you please enter this correctly as y1 equals x squared minus x minus 6 and divided by x plus 2. Make sure that you enter it in your calculator like that, and then you're going to go to table. Then you're going to put this because -2.01 is even closer to -2. Our output value is -5.01. then negative 2.001, and our y value is negative 5.001. And then we're going to have negative 2.0001, and our output value is negative 5.0001. Now, a lot of you guys are wondering where you're seeing this on the calculator. When you enter these values into your table, when you enter these values, these input values into your table, when you enter these input values into your table, the output values will not show it as far as you need to. So what you need to do is look at the bottom of your screen on your calculator, and you will see those values. So now, what have we just done? We've just found the limit as x approaches negative 2 from the left of x squared minus x minus 6 over x plus 2, and we found it to equal negative 5. So now we're going to go back up to the top, and we're going to use the table from the right of negative 2. That's why we put the little plus after it there. And we are finding the limit of the function f of x. So to the right of negative 2, we're going to have negative 1.9. And our output value is negative 4.9. We're going to get even closer, 1.99. And our output value is now negative 4.99. Then negative 1.999, and our output value is negative 4.999. And then negative 1.9999, and we get negative 4.9999. And I hope you can see that this side is also converging to the same output value of negative 5. So we have to then show our right limit. So the limit as x approaches negative 2 from the right of x squared minus x minus 6 over x plus 2 is also equal to negative 5. So if you'll recall from the definition of a limit, if the left limit equals the right limit, then the limit exists, and the limit is that value. So the limit as x approaches negative 2 of x squared minus x minus 6 over x plus 2 equals negative 5. So what we've just shown is numerically, okay, we've just shown numerically the limit. Let's see if we can't see this whole page. No? Okay. No? Okay. Well, you can also see this in your notes, but if you'll look here, we're determining numerically. We enter the function into our calculator, into y1. We go into our table, and we type in our values. But this is how we actually show our work. All right? This is numerically determining a limit. But in this section, we're also going to look at the algebraic. All right? So we're going to algebraically determine limit as well. Now we're going to be using some rules here, and this comes from your text from pages 26 through 28. So we've looked at limits numerically, now we're going to look at limits algebraically. The first algebraic rule we're going to look at is the replacement rule. And what the replacement rule says is if x equals c is a valid input for f of x, then the limit as x approaches c of f of x equals f of c. It simply says If it's valid, if we can plug it in, we'll plug it in, and that's going to be our limit right there. Okay? All right. That is the replacement rule. All right. Now the next rule that we're going to see is the constant rule. So we've seen the replacement rule. Now the constant rule says if f of x equals a constant c, then the limit as x approaches a of f of x equals that constant c. Now that's easy to see, ladies and gentlemen, if you simply remember a constant graph, right, looks like this. So no matter what our x values approach, our output values will always be that constant c. So that's actually pretty simple to see. The next rule is the sum and difference rule. Now the sum and difference rule says if y equals the sum or difference of two functions, then the limit as x approaches a value of f of x plus or minus g of x will equal the limit of f of x plus or minus the limit of g of x. Now what does that mean? That means that the limit of the sum equals the sum of the limits. Then the next rule, which is called by the textbook the constant multiplier rule, or as I often refer to it as the coefficient rule. And it says if y equals a function that has a constant multiplied in front of it, and we'll call that constant k, then the limit as x approaches a of that constant times f of x equals that constant brought out in front. Okay? Now those are the rules. So we have the constant rule, the replacement rule, the sum and difference rule, and the coefficient or constant multiplier rule. Now we're going to look at another rule called the cancellation rule. Now the cancellation rule is a little long rule. Now once I introduce all the rules to you, then I'm going to show you some examples. If f of x is a rational function such that it can be simplified to a function that looks like g of x, by factoring and canceling, then we can come up with this. If x equals a is not a valid input to f of x, but becomes valid as an input to the simplified f of x, g of x, then the limit as x approaches a of f of x will equal the limit as x approaches a of g of x which would equal g of a. That's the cancellation rule. And then we will have the product rule of limits. The product rule of limits says the limit as x approaches a of f of x times g of x will equal the limit as x approaches a of f of x times the limit as x approaches a of g of x. That's the product rule. And then we will have what we call the quotient rule, which says the limit as x approaches a of f of x over g of x will equal the limit as x approaches a of f of x over the limit as x approaches a of g of x. All right, so this is a whole bunch of rules here. Let's take a look at them again. We've got the replacement rule here. We've got the constant rule here. We've got the sum and difference rule, the constant multiplier rule, the cancellation rule, the product rule, and the quotient rule. So now let's take a look at one example in particular. The one that I wish to look at, first of all, is a linear function here. Okay? So if f of x equals 2x minus 3, and I wish to find the limit as x approaches 3 of 2x minus 3. Is 3 a valid input? In other words, can we plug in 3 for 2? Yes, we certainly can. So it's simply 2 times 3 minus 3, so we get 6 minus 3, so the limit is 3. That's an example of the replacement rule. Okay? Let's look at another example here. The limit as x approaches 7 of 12. Now 12 is a constant. No matter what you plug in for, it's always going to be 12. Let's look at another example. Now this next example we're going to look at is the replacement rule. We're going to look at the sum and difference rule as well as the cancellation rule. And I want to look at a function that is familiar to us. In fact, we just did it numerically a few minutes ago. Now, is negative 2 a valid input to the function the way that exists? No, it's not, because we can't plug negative 2 in down there, because if we plug in negative 2, we have 0 in our denominator, and we can't have 0 in our denominator. But we can cancel by factoring. The numerator factors into x minus 3, x plus 2, and the denominator is x plus 2. Yeah, I know. You didn't think that you thought you were finished with factoring, but not quite. Not at all. Now, if you look, the x plus 2's will cancel. So now we have our limit as x approaches negative 2 of x minus 3. Now, notice, I have kept the limit in front. I've kept the limit in front because I have not applied the limit yet. Now, I can apply the replacement rule because negative 2 is a valid input. So we can plug in the negative 2 for the x because it is a valid input. So we have just found the limit. This is an example of the cancellation and then replacement rule. It's an interesting rule, all right? Because we can replace it. Now we know that the limit is negative 5 because we just showed the limit as negative 5 by using the numeric method through the table. Okay? The thing is, if we look at this as a graph, okay, this right here, when we have simplified it, the simplified form is y equals x minus 3. We all know what that looks like. That's a function, has a y-intercept of negative 3, a slope of 1, but at the point negative 2, 5, we have a hole. Now let's remember, as the function is approaching negative 2 from the left, all right, as x is approaching negative 2 from the left, the function is approaching negative 5 from the left. As the x values are approaching negative 2 from the right, the function is approaching negative 5 from the right. The limit from the left equals the limit from the right, so therefore the limit exists, and the limit is negative 5. But is this function continuous at that point? No, it's not, because the original function does not exist at negative 2, because we can't plug that negative 2 in right there. So, in summary, left limit equals the right limit, the limit exists. All right? Then we can look at algebraic methods. Now there's an addendum to this that I want to take a look at real quick. If I have f of x equals x squared plus 1 over 5x squared minus x minus 6. Now if I ask you to find the limit as x approaches infinity of f of x, you would know that this equals 1/5. Now how would we know that? Because what we learned a long time ago, our horizontal asymptote for this is y equals 1/5. How do we know the horizontal asymptote is y equals 1/5? Because the degree of the numerator, the degree of the top equals the degree of the bottom. And if the degree of the top equals the degree of the bottom, then the horizontal asymptote is the ratio of coefficients of those terms. So that's how we determine limits involving infinity. So I wanted to do one more limit involving infinity here. Now that concludes the lecture for 1.3. And so we're done.